Assalamualaikum and hello everyone. Today we group 3 we going to do presentation about donation compound of the lanthanoids complexes with lanthanoid 3 and lanthanoid 2 or lanthanoid 4. Before we start our presentation, my name is Ghurran bin Hashim. My matrix number is 200824.
My name is Nur Azmina, binti Mohd Azman, and my matric number is 200827.
Assalamualaikum and hi everyone. My name is Nur Akilah binti Mohd Bashari. My matrix number is 202917.
In this presentation, we are divided into 6 contents. First, introduction. Second, complexes of lanthanoid 3. Third, complexes of lanthanoid 2 or lanthanoid 4. Fourth, reference. Fifth, Kahoot session. And lastly, Q&A session. For my part is introduction. Complexes. The lanthanoid do not show much tendency to form complex due to low charge density because of their size. However, the tendency to form complex and their stability increase with increasing atomic number. The lanthanoids are moderate in their complex forming ability, which increases to the right. Next slide. Even though the positive ion have a high charge to plus 3 on them, their size is very large. The charge to radius ratio becomes small, yet its ion have less tendency to form complex. For example, the stable complex are known with gelatin ligand such as EDTA, oxalic acid, and acetic acetone. There is a general decrease in complex formation with a specific ligands from lanthanoid 4 plus to lanthanoid 2 plus as charge decreases. Let's move on to the next slide. Donation number. The complex chemistry in aqueous solution is dominated by hard donors, especially oxygen-based ligand, but ligand with other donors atoms such as nitrogen form stable complex in non-aqueous solvent. The lanthanoid aqua ion has a donation number of 9, decreasing to 8 for the later letters. Then the higher donation numbers of up to 12 are possible with ligand with a small bite such as nitrite. Then bi and detented nitrogen donors ligand like PP and terpene form high donation number complexes that often exhibit subtle variation in structure with choice of lanthanoid and solvent. Lastly, the low donation number can be achieved using very large amide, hydroxide, and alkyl ligands when value as low as 2 and 3 are possible.
Here is a short video of lanthanoid introduction.
The lanthanoids are a series of elements characterized by their unique optical, magnetic, and catalytic properties, which makes them well suited for various technological applications. In particular, lanthanoid complexes with linear geometries are desirable targets for superior single-molecule magnets, which are materials that can store magnetic information up to a characteristic temperature. Since the electronic structures of lanthanoids are dictated by coordinated ligands, their magnetic properties depend upon the geometric structures of complexes. To map this relation, a group of researchers from the University of Manchester have conducted a study of the electronic properties of lanthanoid ions in their most stable +3 oxidation state, bound to only 2 or 3 donor atoms. The team studied the effect of geometrical changes in lanthanoid complexes with 2 nitrogen donor ligands, going from linear to bent. Interestingly, they noted that in the solid state, one of the complexes exhibited electronic properties similar to its 3-coordinate halogenated parent complex, rather than the axial ligand field behavior that was predicted. Furthermore, changes in the electronic properties of this complex in solution correlated with variations in geometry induced by the change in environment. Since bent lanthanoid complexes often show inferior single-molecule magnet properties over linear analogues, this study sheds light on the factors that give rise to less bent structures. This will facilitate the building of molecules with geometrical features that maximize desirable magnetic attributes, which can inform the next generation of computational and technological advancements, including high-density storage media. So, much like us humans, the shape of a molecule and what it surrounds itself with dictates its behavior more than its own identity.
Next, I would like to pass presentation to Akilah.
Thank you, Ghurran. Next, I will proceed with the complexes of Lanthanoid tree. Complexes of Lanthanoid tree. An abundance of Lanthanoid tree complexes are formed with anionic polydentate ligands containing oxygen atom donors suited for electrostatic bonding. Coordination numbers usually exceed 6 and the ligands adopt geometries that minimize interligand repulsions. Next, with the aqua ions L and OH2N 3+, the coordinate numbers and structures of complexes vary across the series, from the left to the right periodic table. The small terbium cation YB3+, forms the 7-coordinate complex YB acetone 3OH2 with a monocapoid trigonal prism structure 6, shown in the slide. And the larger La3+ is 8-coordinate in La acetone 3OH22 with a square antiprism structure 7, shown in the slide. Therefore, a square antiprism imposes less ligand repulsion than cubic geometry. Next. Many lanthanoid complexes are formed with crown ether and beta diketonate ligands. Partially fluorinated beta diketonate ligand CF3COCH-COCF3-, nicknamed FOD, produce complexes with Ln3+ that are volatile and soluble in organic solvents. Volatility of these complexes are used as precursors for the synthesis of lanthanoid containing superconductors by vapor deposition. Moreover, charged ligands generally have the highest affinity for the smallest lanthanoid 3+ ions, and the resulting increase in formation constants from large, lighter lanthanoid 3+ to small, heavier lanthanoid 3+. This provides a convenient method for the chromatographic purification of these ions, as shown in this figure 23.13. Before ion exchange chromatography was developed, tedious repetitive sterilizations were used to separate the elements. The coordination of lanthanoids is a flourishing field of research that owes great deal to their applications in bioimaging, as either optical or magnetic tracers, to attach a target functionality, such as an antenna or bioreceptive group, to a polydentate or macrocyclic ligand that forms a strong nullable complex with the lanthanoid. Many robust complexes are based upon a macrocyclic scaffold, for example, being one in which fluorescence is attached to cyclane. This is the structure of cyclane. Deal with bioimaging in more detail. Unlike aqua ions, which exchange water molecules on the NS time scale, many macrocyclic complexes have exchanged half-life that are measured in years. Next, the presentation will proceed by Azmina.
Thank you, Akilah. So now I'm going to present about the complexes of Ln2 or Ln4. So this is the table of the standard potentials for lanthanide 3+ or lanthanide 2+ ion redox couple could be used for predicting the stability of lanthanide 2 complexes. Okay, europium with the symbol EU here is the only lanthanoid showing an extensive aqueous chemistry in the 2+ oxidation state, whereby it has a property that originates in its relatively high I3 value and attributed to the relative stability of the 4F7 configuration. And many EU2 complexes can be conveniently prepared in water by adding a polyanionic ligand to a solution that consists of EU2 plus ions, or through chemical reduction of the EU3 plus complex. Then the complexes of EU2 with ECTA or DTPA are powerful one electron reducing agents. The reason for this are because they have much more negative reduction potentials than EU2 plus, and due to the preference of the polyanionic ligands for the 3 plus oxidation state. And yet there are slow to evolve H2. After that, the most important coordination complexes of lanthanide 2 are those synthesized with non-reducible genating ethers as solvent. And starting from the lanthanide diiodide, a variety of highly reactive Ln2 ethoxy complexes are formed. And then the stability order from samarium to samarium and then dysprosium, tracking the trend in standard potential table. And samarium diiodide, SMI2, is commercially available as a deep blue tetrahydrofuran solution containing species formulated as SMI2THFN. And the iodide ligands occupy in the axial positions. Next, the dark green crystal of DMI to the ME3 are produced by comproportionation of the MI3 and powdered TM in dimethoxyethane. So these are the complexes that are powerful one electron reductants in non-aqueous etheric solvents. And then the complexes also are useful reagents for reductive CC coupling reactions. An example being the formation of tertiary alcohols from alkene halides and ketones. Also, the carbon-carbon coupling reactions can occur between the ligands, and the reaction of TMI2 with pyridine results in formation of the complex, in which the product is the 1,1-dihydro for 4-bipyridine reach the 2-samarium-3 metal. Cerium-4 also has an extensive range of coordination chemistry. Apart from the CeNO3 6 2-, most cerium-4 complexes are based on alkoxide or carboxylate ligands, and a binuclear cerium-4 complex with bridging oxido ligands is formed by reacting a tris-amido cerium-3 precursor with oxygen. So for the references, these are the list of references that we use to prepare our slide.
Next, we got 2 sessions, which are Kahoot session and Q&A session. That's all from us. Thank you.
Thank
Thank you.